Good evening, everyone. This is the NPTEL problem solving session for the course Robotics Basics with Selected Advanced Concepts. And this is the session for week 11 and 12. And I will be going through the lecture notes of this week and discussing some of the assignment problems, not the solutions, but how to approach them and how they relate to and how, to the lecture notes. So let us start with the lecture notes. So this week's lectures were about over-constraint mechanisms and doing kinematic and static analysis of those kind of mechanisms, over-constraint mechanisms. And again, there was a discussion about making deployable structures from so, these kind of mechanisms, over-constraint mechanisms. Okay, so the first lecture, over-constraint mechanisms, goes over some of the basic concepts that were defined earlier but have to be changed for over-constraint mechanisms, like degree of freedom. Okay, because to calculate degree of freedom, the usual approach that is taken is using the Grubler-Kutzbach's criteria. Okay, but this only takes into account the number of links and number of joints. Okay, it does not take into account any special geometry. Okay, and due to this reason, for the kind of mechanisms that were discussed in this week, had their degree of freedom less than one. Okay, it was a fractional degree of freedom, and of course, it does not make much sense for any system to have a fractional degree of freedom. But this is what this criteria actually leads to, as you can see in some of the examples that have been given. Okay, and like in your assignments problem also, you might see that when you calculate the degree of freedom, okay, it will come out to be different than just one, right? Yeah. So again, there are many different kinds of orchestration mechanisms. Some of the examples were given here. Okay, like this side there's this RPPR mechanism, and there is an RRPR mechanism also. Okay, and there is this 4R linkage, spatial 4-bar. Okay, mechanism with just a revolute joint, but the joint, all the joint axes are not parallel, so the whole mechanism is not in a plane. Okay, it can go out of the plane. Okay, so this kind of mechanism is an over-constraint mechanism. Okay, so there are other uh, types also, like there are over-constraint mechanism where you see the motion. So one thing is where you see the motion happening, but the um, this Grubler Kutzbach criteria, it gives you a degree of freedom of 0 or a negative degree of freedom or something that does not make sense. Okay, and so these are used for making deployable pantograph. Like this is also an example. Okay, of our customer the deployable pantograph masks that are used in space applications. Okay, so these are systems of this sort. Okay, so these are given in the image here. Okay, so they use the pantograph mechanism, and so that they can collapse when they need to be transported, and then they can expand. Okay, or they are essentially deployed when they reach their target location. Okay, so then there was discussion about how does one actually calculate degree of freedom and mobility in case of these over-constraint mechanisms, and like there were many approaches that were given. Okay, one was the Grubler-Kutzbach. Like this was shown that this fails. Okay, so now one criteria that is used in that has been taught in this week is the nullity of the constraint Jacobian. Okay, it is not any Jacobian matrix. Okay, it is the nullity. It is the dimension of the null space of the Jacobian matrix. Okay, because the dimension of the null space of the Jacobian matrix does give the number of degree of freedom of the number of, yeah, the degree of freedom of the whatever system or mechanism you are evaluating it for. Okay, and then there are some other criteria also, but for them, these references have been given. So you can go and check them out. And then uh, continuing on the modeling and analysis of these kind of deployable structures. Okay, so then there were some applications like in space applications, they have to have small payload. Okay, so that's why this kind of mechanism, this it will come now. Yeah, so this kind of structure needs to be as small as possible so that it takes very less space when being transported, and then it can expand when it reaches its target. Okay, and then modern communication systems have large appendages. Okay, because again, for example, a satellite has a okay, so suppose there is a satellite and it has, okay, solar panels, okay, at both of its ends. Okay, so this now is a very wide system. Okay, but it cannot be transported like this while it is being sent from Earth. Okay, so both of these, all of these things have to be somehow folded into a very small packaging. Okay, a very small packaging so that it takes up less space. Okay, because again, the space is limited in space vehicles. Okay, so these kind of appendages, they need to be folded before they can be sent. Okay, and this kind of mechanism that helps you fold and release links or different parts of the same mechanism leads to an over-constrained system. Okay, uh, yeah, and then when there are large number of links and joints are present. Okay, and when there are essentially when there are large number of links and joints, but they are interlinked very heavily with each other. That is when they give rise to a deployable structure. One example is the mechanism that was given above. Yeah, it will. Yeah, let's show the mechanism. Okay, so this D. Okay, so this campus bumster focal mechanism. Okay, so this is again an over-constrained mechanism, and you can see that there are many links and many joints. Okay, but they are interlinked with each other. Okay, so this particular joint T, okay, it is a common joint for four different links, right? And most of the joints, like this Q, the C, and B, so they have multiple links. They're attached to multiple links. Okay, so again, just having large number of links and joints does not lead to an over-constrained mechanism, but if they are interlinked together heavily, that will lead to a over-constrained mechanism. Okay, and during deployments, they all behave as one degree of freedom mechanism. Okay, like that, we will see how that happens. Okay, and yeah, so the main ones are coilable. Okay, where you can just rotate them and they shrink axially like a coil, and pantograph masks. Okay, antenna and solar panels, and again we discussed about both of these, antenna and solar panels. Okay, so yeah, so this is the pantograph mechanism that we were talking about. So at one end it is just a revolute joint that is grounded, and at the other joint it is a revolute joint that can slide on the ground. Okay, so when you actuate this, or if you move this slider joint horizontally on the ground, the height of both of these arms decrease. Okay, so again, you can see that it is essentially a one degree of freedom mechanism. Okay, so this is the basic. This is the most basic structure that is used in these masks or deployable masks. Okay, so in coilable pantograph mask mechanism. And okay, so yeah, again, it's also called the scissor-like element. Okay, so this SLE type element has been discussed in great detail in this whole week. Okay, and this shows that how the threads are passed through all the joints to actually actuate it. Okay, so again, it is all using a single thread. Okay, the actuation of the complete mechanism. And then there is a ring pantograph. Okay, and these kind of pantograph mechanisms, they are also used to make 1 degree of freedom walking robots. Okay, so uh, they are called walking contraptions also. If you look on the internet for, okay, walking contraptions. Okay, so some of them are based on the pantograph mechanism, right? And you must have seen many of those actually. Like there is a there is a base, okay, and then there are many links like this that are arranged such that they move with a specific phase difference that gives rise to at both the ends, at both the sides. Okay, so they are arranged such that they are run by a single actuator. Okay, they are run by a single actuator. Okay, but due to the phase difference between them, it leads to a net motion in the forward or whatever direction it has been designed for. Okay, so yeah, so these kind of pantograph mechanisms can also be used for making legged robots. And then there are different examples of pantographs, like this is the scissor pantograph, the SLE, the ring pantograph. Okay, and then there are circular pantographs. Okay, with ring and radial tension membranes. So there are different kinds of these over constraint mechanisms that you can make, okay, depending on where the links are facing and which members are being tensioned or displaced to produce motion. Okay, and then again, there are different types of coordinates. Okay, so one is the when studying these kind of four constraint mechanisms, one is the relative coordinates with respect to the previous link. So that is the good old Leavitt-Hartenberg parameters coordinate system that we have studied. Okay, one is the reference point or absolute coordinates of each of the link. So for each link, you take, so these are also called the maximal coordinates. Okay, so you take the center of mass, position, and orientation of each link separately, and then you study the whole system with these variables. Okay, and then there are Cartesian or natural coordinates. Okay, so where the reference points are moved to the joints. Okay, so for example, this third case, okay, the C, so you only take the x and y coordinates of the joints. Okay, and the orientation information is embedded into these coordinates. Okay, so again, when you choose any of these coordinates and you try to write the kinematic equations for these systems, they will lead to some loop closure constraints in all of them. Okay, and these constraints, okay, the number of these constraints is what leads to them being over constrained, because the number of constraints is basically more than the theoretical number of the degree of freedom of the robot. Okay, and when we do not know the actual number of degree of freedom, okay, so this is when the idea, so these are this is when the idea of the nullity of the Jacobian comes in. and that has been discussed afterwards. Okay, so this in this section, it has been discussed that how do you actually write the constraint equations using natural coordinates. You can use any of the coordinates, but when you change your coordinate system, then you have to also change the way in which you write your constraints. Okay, because see, when you take Cartesian coordinates, it becomes really easy to define the length between the origin, let's say O1, and the joint x1 y1 as the length constraint, right? Or the angle between x1 y1 and x2 y2 as another constraint, the joint constraint, right? Because this line will always be along this joint. So these kind of constraints are easily written in Cartesian coordinates or natural coordinates, whatever you want to call it. And this is just how you write the constraint equations for some of them. Okay, for some of the constraints. Okay, and then when you need to find the Jacobian, and why find the Jacobian? Because they're trying to find the degree of freedom. Okay, so how that is done is, okay, so it is the BOF for over constraint mechanisms. Okay, and how they are calculated just tell this take okay, so degree of freedom for over constraint mechanisms. Okay, and how it is done is like you have a complete vector of all the constraint equations given your choice of coordinates, right? So this is a vector of all the coordinates, this vector x. Okay, and since given this constraint vector, you can write the Jacobian corresponding to this particular constraint vector. Okay, and what you see is that the rank of this matrix, okay, or whatever you can see the dimension of the null space of J. Okay, that is also shown as nullity of J. Okay, so this number gives you the degree of freedom. So this is what has been told here. Okay, so the dimension of null space is same as the degree of freedom, and you can calculate the dimension of the null space by calculating the rank and just reducing it by the whatever row rank or column row dimensions or column dimensions of this matrix. Okay, since the null space and the row space are orthogonal to each other, so you will uh, subtract the rank from the dimension of the row space to get the dimension of the null space. Okay, and then again there is just this discussion about how to proceed in case of multiple constraints. So again, at each step you keep adding one of the constraints and you keep reevaluating the Jacobian, and for whichever constraint, the nullity of J does not change even after adding that constraint in your constraint vector. Okay, because that will cause your size of the J to change. Because if that does not reduce the null space dimension, that means that that particular constraint is redundant. Okay, because constraint, if it does uh, introduce an actual constraint, that constraint should be on the degree of freedom. And since the dimension of the null space corresponds to the degree of freedom, it should reduce if it has to have any effect of the constraint. Okay, so the final dimension of the null space of J, when you have taken into account all the constraint, is essentially the degree of freedom of the system. Okay, and then there was discussion on kinematic and static analysis of these kind of four constraint mechanisms. Okay, and yeah, there is this algorithm that was given above also, how to calculate the degree of freedom for these kind of mechanisms. So again, just keep taking constraints, keep stacking them up, and keep calculating the null space, keep calculating the dimension of the null space, and the final dimension of the null space is the degree of freedom. Okay, and again, you have to um, leave out the constraints that do not change the nullity. Okay, because they are redundant, they are not required. Okay, they have already been taken into account by some other constraint equations above, or a combination of some other equations, constraint equations, right? And then there is an example for three slider mechanism. Okay, so again, once you take different constraints into account, how does the size of J change and how does the size of the null space change, right? And you see at this third and fourth line, the null space does not change even after introducing the dot product for the link n minus p minus npq. Okay, so this link npq, okay, this has already been taken into account when you take link rij and klm. Okay, so that is why it does not cause any further decrement in the dimension of the null space, and that is why this particular constraint is redundant. And then there is another example of the mechanism that we saw above that has many links and many joins, right? And so, like you can go through these examples. Okay, so like what you need to keep in mind is how to write these constraint equations. Okay, and how to write these constraint equations has been given above, right? Here, like how to writing constraints with natural coordinates, right? If there is a linear constraint, right? There are three collinear points. Just use this. That yeah, all of them lie along a line. Okay. So, and then yeah, so there was the static analysis of this scissor based mechanism, the pantograph mechanism based masks. Okay, and what is static analysis is basically the static force analysis. Okay, like what is the elongation in the th thread for the load, right? If I'm not wrong. Yeah, so what is the elongation for a particular load? Okay, so the member stiffness matrix for this particular SLE based mast is this, right? So the stiffness for each matrix. So every element has been treated as a beam, as a beam element. I think it was written also somewhere. So yeah, whatever. And then using the constraint, the force, external force, and the load are related by the Jacobian. Again, the constraint Jacobian, as we've seen in the case of manipulators as well, right? And then when you relate the load with delta x, or the change in your coordinates. This is what you end up with. So this is the effective stiffness matrix for this particular mechanism. Okay, and using this stiffness matrix, yeah, like you can calculate the rank also, because this rank of Km will be the same as the rank of J. Okay, and you can consider rotations also. When you consider rotation, and you'll also have to consider the moments. And for rotations, you'll have to consider the rotational stiffness as well for those particular elements. Okay, and the combined stiffness matrix is for both the linear elements and the rotational elements. Okay, and yeah, this is the same thing, that the rank of is the same as the rank of Jacobian matrix, and this is a very small proof for that. Okay, and so this week was more or less about these mechanisms, and if you go through the assignments, so they are all just mostly theoretical questions directly based on the lecture notes or very near to what has been given in the lecture notes. Okay, so if you go through the lecture notes and the lectures, you will be able to do all the assignment questions. Okay, so but yeah, for example, in this question 10, you'll have to think that what is meant by a redundant joint. Okay, so basically the whatever this whatever the constraint introduced by that particular joint, if that does not change, for example, the nullity of the null space Jacobian, that particular constraint, for example, if the link QD is redundant, then the constraint introduced by this link QD, when taken into account to calculate the Jacobian matrix, will not cause a decrease in the rank. Uh, no, or you can also say in the dimension of the null space of the Jacobian matrix, and you can also see that in the notes here. Okay, so whatever you take the joint coordinate as, okay, so like it is given also in example 2. Okay, so basically whenever a constraint is redundant, that means that even if that constraint was not there, the system would move in the exact same way as it is moving when the constraint is there. So basically that constraint is not required, is not playing any role. Okay, yeah, and again, so basically everything is either directly given in the lecture notes or is somehow very closely to the lecture notes. So if you go through the lecture notes and the lectures, you will be able to do all the questions. And if you have any further doubts, you can post them on the forums. I think I will stop the recording here.